Hello, so this is another video on quantum field theory for the gifted amateur, where I go through the book chapter by chapter talking about the key aspects. In this video we're going to look at the Klein Gordon equation, so we're going to be looking at an attempt to bring together relativity and quantum mechanics. An attempt that had some successes, such as being able to describe force-carrying particles like photons and pions, but which struggled to describe matter particles, and we'll talk about why that is, and that will give us a good feeling for kind of what relativistic quantum mechanics has to look like going forwards and where the current problems are. If we stick with very kind of Schrödinger-like concepts, like relating the field described in our quantum mechanical equation to some notions of probability. So that's what we'll look at in this video. It's worth saying that the book doesn't go into actually the successes of the Klein Gordon field very much. In fact, I don't think it goes into the successes of the Klein Gordon equation almost at all in the current chapter I've been looking over to make this video. But I thought it was worth including because often the Klein Gordon equation gets a bad rap for being a failed equation, and it's far from that. As we'll see in this video, it's just incomplete, and definitely its successes were different than what the equation was actually intended to do. The equation was more intended as a generalization of Schrödinger's equation to describe relativistic matter particles. It turned out not to be so great at that, but it did a few really good things, which we'll explore in this video. So to start with the Klein Gordon equation, because it takes inspiration from the Schrödinger equation, we do a very similar recipe. So one way to derive the Schrödinger equation is you essentially take the equation for the classical kinetic energy of a particle in terms of its momentum, but then you replace the energy with the Hamiltonian operator and the momentum, the classical momentum, with a momentum operator, and that way you kind of quantize these classical observables leading to a quantum theory. And that's how you get to Schrödinger's equation. So you can get to the Klein Gordon equation similarly. It's just because Klein Gordon was interested in bringing relativity into the picture, instead of starting with the classical equation for the kinetic energy of the particle, what Klein Gordon, Klein Gordon are a couple of people, but what the Klein Gordon equation can be reduced to is essentially a quantized form of the total relativistic energy of a particle, which is like the relativistic version of the kinetic energy of a particle. It's a relativistic version because, if we ignore relativity, the only energy a particle can have is its kinetic energy. But when we're doing the relativistic energy, we take into account relativistic kinetic energy and also energy associated with rest mass, which is an energy that relativity predicts. But anyway, to get there, to quantize this expression for relativistic energy, we have to have operators for energy and momentum. We use the same operators that Schrödinger used, and so we're going to briefly review what they are and why those operators have the form they do. So to start with, if we're going to describe a field or something, be that a field like a plane wave associated with the wave function for a free particle, or even a field like the electromagnetic field, which we will see as a solution to the Klein Gordon equation. Generally, these fields are described by something that's called a plane wave, and a plane wave has this kind of form. If you've seen kind of lots of engineering textbooks, they tend to represent waves in this kind of form because it's perfectly capable of describing a generic plane wave, where k is a constant relating to the wavelength of the wave and omega is a constant relating to the frequency of the wave. And, you know, psi can be interpreted as the kind of displacement of a particle on that wave from its equilibrium position. But because psi is complex, it'd be displacement in some kind of complex space. But that's a way to think about, you know, the wave function visually anyway. And if we're going to look at operators for energy and momentum, we have to consider what constant in our expression for the plane wave does energy relate to and what constant does momentum relate to. Well, it turns out momentum relates to k, relates to the wave number of our plane wave. And you can derive this relation between the momentum of a particle and the wavelength if you send non-relativistic electrons or any particles with a rest mass through double slits. They'll diffract and produce an interference pattern, and from looking at that interference pattern you can deduce the value for k associated with the wavelength of the waves that are kind of diffracting and interfering. And if you've done a course on on physical optics, you'll be familiar with this. But you can do this experiment for electrons with many different kinetic energies or momentum, and if you do that, you'll find that there is this relationship, this quite simple relationship between the momentum of the electron and its associated wave number, k. Now, the other constant apart from k in our plane wave is omega, and omega, it turns out, relates to the energy of a particle, and you can do this through, well, you can see this through the photoelectric effect, where you shine photons at a metal surface, and free electrons on the metal surface can get liberated if the photons have enough energy. And by looking at what kind of frequency of light, in other words, frequency of the photons, will cause the electrons to be emitted, and also how the energy of the emitted electrons relates to the frequency of the incoming light, you can derive, you can experimentally get this equation which relates the energy of the particles of light, so the energy of the photons, to the value of omega, so the angular frequency of the electromagnetic wave. And if you want to quantize energy and momentum, we need operators for these. Well, when we are talking about operators, we're talking about getting an eigenvalue equation. And you can see that kind of if we define the energy operator to be the Hamiltonian, and we say the Hamiltonian is IH bar multiplied by partial derivative with respect to time, then when we operate the Hamiltonian on our plane wave, we will get out of that the energy of our plane wave. So clearly the Hamiltonian is kind of the quantized form of the classical kind of energy of a particle. And similarly with momentum, you can work out that the momentum operator is just minus IH bar times partial derivative with respect to x, your spatial position coordinate. Now, I went through that fairly briefly because this really is kind of something that is used to derive Schrodinger's equation, because if you now take your operators, or Hamiltonian and your momentum operator, and substitute them for kinetic energy and momentum of a classical particle, you'll get Schrodinger's equation. So kind of this kind of stuff is kind of more quantum mechanics and quantum field theory, and so I've gone over it quite quickly. But we can take these operators and now apply them to our expression for the relativistic energy of a particle to get the Klein Gordon equation. So something that unites quantum mechanics and relativity instead of quantum mechanics and classical mechanics. So firstly, because relativity has through it the speed of light, and because quantum mechanics has through it a constant called h bar, these constants would appear with many, many different powers all over the place in our quantum mechanical equations if we're looking at relativistic quantum mechanics. And that would make interpreting the equations quite difficult because they would kind of hide a lot of physics and make the equations far more complicated in terms of the core physics than they actually need to be. So what we tend to do is when we're doing relativistic quantum mechanics, and particularly when we're doing quantum field theory, we use something called natural units, where we say c, the speed of light, is equal to 1 and h bar is equal to 1. Now importantly, we're not only saying the value of the speed of light is 1 unit, what we're saying is the speed of light has no units, so we define c to be the number 1 with no units attached. Similarly with h bar. Now that might sound strange, but we can do that. We have to change the units of other things to make this work, but we can do that. For example, if we look at the speed of light, well, it's a velocity, and it's a velocity kind of linked to relativity. But in relativity, we know time and space are semi kind of equivalent in a lot of ways. If we think about, the fact that the space-time interval matters, but the space or time-like part of ball position can kind of change between observers, it means that kind of, space and time are kind of the same thing. And so if speed is like distance and space over interval and time, then speed should be, if we think of it in terms of relativity, speed should be dimensionless. It shouldn't have any units because the units of space and time should kind of be the same. So it might sound strange to set c equals to 1 and get rid of the units, but it is justified in terms of relativity. And as for setting c to equal 1 in terms of any other number, well, we're free to pick whatever number we want, really, providing we calibrate all other speeds accordingly. So we can pick c equals 1. And you can use a similar argument, well, you can use a different argument, but, it reduces to the same thing where you can go, well, h bar we can say is just equal to 1. Now, as I said, we need the equation for the relativistic energy of a particle, where if we're ignoring factors of c, because again we're setting c to equal 1, it turns out the relativistic energy is given by E, where E squared is equal to P squared plus M squared. For those of you interested in relativity, this essentially comes from considering the invariant quantity associated with 4 momentum. And that's something I will come on to in a couple of videos time in the special relativity playlist. So if you want to know where this equation comes from, it's going to be on the special relativity playlist not too long. But for this video we can just take it to be true. So we have an equation for E squared, where E is the relativistic energy of a particle, and to turn this into quantum mechanics we quantize it. So if we quantize it, we replace E with our Hamiltonian and replace P with our momentum operator. And then if you substitute in the expressions we had before, again, remembering we're setting h bar to equal 1, so factors of h bar will seemingly vanish, then we end up with this expression for a field phi. Now, in quantum mechanics, the field is the wave function of a particle, so we use the symbol psi, which looks like a trident. But when we're doing fields in quantum field theory or relativistic quantum mechanics, to make it clear, we're not talking about the wave function. We have to use different Greek letters, so we use phi. So phi is our quantum field. And it will turn out, as we'll see later on, that we can't really think of this field in terms of very easily probability anymore. But it's essentially a field which obeys, firstly, the relativistic equation for energy, but also, in some way, quantizes this relativistic energy, or is a field we get when we're thinking of acting on operators which quantize this equation. Because our operators have to act on something, and so they act on a field which we call phi, and I'll call phi the Klein Gordon field, but on our bottom equation in the box we have the Klein Gordon equation. However, because it's relativity, well, it's good that we've got second order derivatives in time and space. You know, this means that this definitely looks far more compatible with relativity than the Schrödinger equation. However, we've still written it as if time and space are separate things. So to deal with that, we just define something which is like the version of the Laplacian operator, but in 4D space-time, which is like nabla squared. And you can think of it as kind of like the scalar product of the full gradient with itself, but in the context of special relativity. But for those of you who do not want to get kind of too stuck in the whole relativity thing, essentially nabla squared is just equal to the partial derivative in time, is equal to the second order partial derivative in time minus the second order partial derivative in space. Or if we're dealing with many dimensions of space, it'd be minus the Laplacian operator. So this is essentially in our top equation in the blue box. We have a more elegant way of writing the Klein Gordon equation that makes special use of kind of ideas in kind of relativity, like the full gradient or calculating the scalar product in space-time of a 4 vector. It's just a more elegant way to write it, really, for our purposes. So we can now look at possible solutions to this Klein Gordon equation. Now, the first solution is when m is equal to 0. So when the particle this field is describing it doesn't have any mass at all. Well, if we start with the Klein Gordon equation in its not so elegant form, we have this. But if we now kind of like essentially say m is 0, then our inhomogeneous part of our equation, if you like, goes away, and we're left with an equation where essentially we have a wave equation. If you look back earlier in the playlist, we talked about the wave equation, both for the wave on a string and also when we're looking at Maxwell's equations, and this is the wave equation. And if you bring back your constant C and H bar, you'll find that actually it's the wave equation for a wave that moves at the speed of light. So in other words, the Klein Gordon equation can describe, if you like, the field, the electromagnetic field associated with photons, so particles of light. So this field isn't seemingly describing, at least when we look at m equals 0, particles like electrons or protons or neutrons, but it is describing particles, albeit a particle which is carrying a force. So not a matter particle, but a particle in this case that is carrying the electromagnetic force. And it would turn out also when we look at cases where m doesn't equal 0, again it's describing force-carrying particles, but particles that are less talked about than the photon. So when m doesn't equal 0, we again go back to our full Klein Gordon equation to start with, but we now can't set m equals to 0. So how do we simplify this? Because at the moment this equation looks really complicated and difficult to solve. Well, I don't even want to set something in this equal to 0. Having all three terms is really difficult. So one thing we can do is consider a field which is time independent. So we set the partial derivative of a field with respect to time equal to 0. In other words, the zeroth components of our full gradient acting on our field is equal to 0. Well, when this happens, the first term in our Klein Gordon equation goes away and leaves us with an equation that relates a field which now will just depend on spatial coordinates. So collectively we can think of, these spatial coordinates as allowing us to plot a point with a vector associated with it in three-dimensional space, which we call the vector r. So our field becomes a function of essentially this vector r, and as I say, it has no time dependence. Well, it turns out that there is a solution to this equation that describes a very real particle. Now, how it describes the particle is a little complicated, because technically the strong force has a gauge boson called the gluon. Now this equation doesn't actually end up describing the gluon properly because the gluon itself doesn't have any rest mass. The gluon neither really obeys the Klein Gordon equation when m is 0, because the gluon has other strange features, like the gluon has itself something called colour charge, so it can interact with other gluons, making it quite different to the photon. But a particle closely associated with the gluon is the pion. So whereas the gluon holds quarks together within a particle made up of quarks, so within what we call a hadron, a pion keeps individual hadrons connected together when they form a large group. So, for example, in the nucleus, the protons and neutrons are all held together by the exchange of pions. So pions are, in a sense, a force-carrying particle. Pions are also, it turns out, mesons, and therefore spin zero particles, meaning that actually the Klein Gordon equation describes these particles extremely well. But that's going into more detail than we need for now. But in a particular sense, pions are force-carrying particles, even though you can also think of pions in terms of matter particles, particularly if you're thinking about things like the production of muons through cosmic rays, then pions are kind of decaying, much like matter particles. So whether a pion is a force-carrying particle is a matter of some debate. It depends on what you mean, but for now we can consider a pion a force-carrying particle, although because it's not a fundamental force-carrying particle, because a pion itself is made up of quarks and matter particles, it isn't a gauge boson, but it is acting as some kind of force conduit for the strong force. So a field is going to relate to the pions, and because the pions are carrying a field, because the pions are, the pions are carrying the force, a natural field associated with the force is a potential. So this field phi is actually going to be the potential energy of the strong force, where the strong force is the force holding, different particles within the nucleus together. So holding our protons and the neutrons together through these pions. But as a technical note, it's worth saying to get our equation for our potential or our field phi, we have to know what the Laplacian operator is for a field in 3 dimensions of space. Well, because we're describing a force, like most forces in nature are radial, and there's no reason to think that the strong force in a nucleus wouldn't be radial, so we might make a guess at a sensible possibility and go where our field isn't just dependent on spatial coordinates, it's radial. So it just depends on the radial distance between, say, 2 particles in the nucleus. It doesn't depend on their relative angular positions. And in that case, the Laplacian operator is written in an equation for 1 over r squared in partial derivatives in terms of r. Essentially, the Laplacian operator, if you're considering it acting on a field where the field is radial, so just a function of your radial distance r, then you get this nice expression for the Laplacian operator acting on your field. And you can now, you can now do various things. One thing you can do is you can solve it, because now this is an equation where phi is just a function of r, and so if you now integrate, rearrange, you can solve this and end up with an expression for your field phi, or in other words, the potential associated with a strong force. But you can also put in a solution and just check it as a solution by substitution. And this is a possible solution. And this solution is called the Yukawa potential. Now V here is the same thing as our field phi, and as I said, the Yukawa potential describes the strong force but between particles within the nucleus, so between neutrons. And one thing you can see with this, well, there's various things to talk about. So one thing is this 1 over r is actually proportional to the mass m that goes into your Klein Gordon equation. So as the mass of the force-carrying particle, so in our case the pion increases, the range of this potential drops, because as mass increases, this exponential decay is going to be stronger. So, the larger the mass of the pion, the smaller the range of the potential. And so the mass of the pion is related to how far the strong nuclear force can act. So if you've got one nucleon and it's kind of interacting with another nucleon by the strong nuclear force, how far apart they can be before the force starts to get, very, very weak. And therefore this determines the mass of the pion, ultimately the maximum size of kind of stable nuclei. And by stable in this case, I don't mean nuclei won't decay radioactively, I mean nuclei won't just naturally break apart. That the nuclei will kind of, won't start disintegrating because they're too large. So this is quite a cool result. Now G is something that tells you it's a coupling factor. It tells you about the strength of the strong force relative to the other fundamental forces in nature. Now the cool thing about this equation is this equation, as I say, it describes a relationship between the mass of the pions and the size of a stable nucleus, showing that the Klein Gordon equation has very real, very important applications. Often the Klein Gordon equation is considered to be something of a failure. It's considered to have not succeeded. However, it does have some very useful applications. And I think the reputation the Klein Gordon equation has for not being successful is kind of unfair. And I feel it's an important lesson for kind of physics to hold on to, that, just because an equation doesn't manage to describe what it was fundamentally trying to describe doesn't mean it doesn't have useful applications or isn't worth investigating or learning. So I personally think the Klein Gordon equation is really exciting. However, now I've praised it, it's time to talk about the very legitimate reasons why the Klein Gordon equation does fail in so much of at least trying to describe, matter particles like electrons and stuff. However, as I've said, the idea of the Klein Gordon equation is a really good idea. Does a lot of stuff great. However, it struggles with matter particles, and the reason that is it ends up predicting that certain particles should have negative probabilities associated with them. However, that's extremely problematic, because negative probability is logically impossible. It's not just physically impossible, it's logically impossible. Because for something to have negative probability, it would have to be less likely to happen than for it to be impossible to happen, which doesn't make any sense. So negative probabilities are a logical issue, indicating that somewhere in the Klein Gordon equation we haven't made so much a physical mistake in our assertions, we made some kind of fundamentally logical error. We've done some piece of maths that seemed logical but for some reason wasn't. And we'll come on to that when we look at an equation that describes matter particles in a much more, it's a lot more successful in that respect than the Klein Gordon equation. So to get to the heart of why the Klein Gordon equation doesn't work for matter particles, we need to understand probability in quantum mechanics and how probability works. Particularly how we get probability from our field, be that the Schrödinger wave function or a Klein Gordon field. Well, probability is something that we can think of as some kind of conserved quantity. Now, in classical mechanics, you're very familiar with physical observables, like energy, momentum being conserved quantities. But in quantum mechanics, thanks to Heisenberg's absurdity principle, those quantities aren't generally going to be strictly conserved anymore. In fact, thinking of any quantity, any physical quantity as strictly conserved in quantum mechanics wouldn't be very realistic. Often, approximately, you can do this to a good approximation, but there are at least logical issues with having a theory which fundamentally presumes observables to be possibly constants for a system if a system is quantum mechanical. So you might ask, well, what is a good conserved quantity in quantum mechanics? Well, a good conserved quantity is probability, by which I mean the probability of something, the probability of us finding the system in one of its possible states at any moment in time must always be 1. We don't know what state we'll find it in, but we have to find it in one of its possible states. So as the system evolves, the state we're likely to find it in might change, so the state won't be a good conserved quantity, but the total probability associated with finding our system in a possible state has to be 1. For example, if we think of a good analogy, if I've got a bag and I fill it with balls and I shake the bag and some balls fall out over time, at any time I might stop shaking the bag and look in the bag to see how many balls there are. And it should be certain that when I do this, it will at least be physically possible to infer how many balls there are in the bag. It would be somewhat absurd if it was logically impossible to say how many balls there were in the bag at any moment in time. So in other words, the probability of there being, a possible number of balls in the bag, if we sum over all possibilities, has to equal 1. So probability is a conserved quantity, and it has to be for purely logical reasons, even in the case of quantum mechanics, which seems so physically unintuitive. So, because of that, we can say something very general about probability in quantum mechanics, which is essentially a very posh way to say probability is conserved, and that is we can make use of something called a continuity equation. Now, continuity equation is traditionally first introduced with respect to classically conserved quantities because those things are much more intuitive. And so if we're considering, for example, the charge that an object has, then, let's say that this object is, say, extended. So it's not a point particle. Let's say, we've got like a piece of paper and this paper is charged. And charge is free to move on this piece of paper. It can't leave this piece of paper. So this piece of paper is a closed system, so the charge has to be conserved on the paper as a whole, but the charge is free to move in different regions of this paper. Well, we can do something. We can look at a point on this paper, or in fact, to be more accurate, we can look at a region in this paper, and we can work out what is the charge density. So how much charge is there per unit surface area in this region? And we can ask, well, what happens if this charge starts to change with time? Well, if it changes with time, because the total charge on the paper has to be conserved, then the charge in other regions of the paper must also change. So in other words, we must have charge either coming in to our region, if the charge in the region is increasing from other places, or we must have charge going out from our region into other regions of the paper if the charge in our region is dropping. And that way charge overall can be conserved. And you can mathematically formalise this by saying the rate of change of the charge density in a particular region of our charge paper has to equal minus the divergence of kind of the electric current in that region of the charge paper. And that minus sign is important because if the charge is increasing, then that must, in a region, then that must mean that charge is being drawn kind of towards that region from other pieces of the paper, in which case you need the divergence to be negative if your kind of charge density increases positive. So that minus sign is important for those reasons. But to bring it back to quantum mechanics, in quantum mechanics, charge is not considered quantity necessarily. Actually, it turns out charge will be, for reasons we'll look at later in this playlist, but we can't take that as a given at the moment. But a considered quantity we can take for given is probability. So instead of rho representing charge density, now rho represents probability density, which in the case of the wave function in Schrodinger's equation is just equal to the wave function squared. I should say the modulus of the wave function squared. But then the devil in the detail of kind of how this probability density has to move in space if the probability density in a particular region increases or decreases is given in terms of our probability current, so not electric current but probability current J. And we can combine actually the three-dimensional probability current and rho, so probability density, into a single 4-vector. So an object with 4 components called J, where it has components J mu. So J naught is the time-like component of J, which is just the charge density, and then the space-like components of J is just, J0 is not the charge density, J0 is the probability density, so it's just equal to rho, but then the other components of J is just our kind of probability current. And the nice thing about setting equal to 0 is it's very reminiscent of a conserved quantity, because it's essentially going, well, it has to be conserved in space-time, because in any region it's allowed to vary in time, but it must change in space accordingly, that we can actually say the kind of the, if you like, space-time version of the divergence of our 4-vector has to be 0. So in that sense, our 4-vector is conserved. And you might ask, well, what's a good expression for the probability current? Well, we're going to, for now, assume, and we'll justify it in a bit, but we're going to assume that we can take the 4 current to be the 4 current from Schrodinger's equation. So in Schrodinger's equation, if you take rho to be the probability density, so the modulus of the wave function squared, you can calculate directly what 3-dimensional probability current would be, and therefore what our 4 current would be. That is what J mu would have to be. And when you do that, you'll end up with this expression, although in the case of Schrodinger's equation, you would have psi instead of phi as your field. But because we're now going to apply this to the Klein Gordon equation, we're going to use phi for our field. And we're just assuming that the Klein Gordon equation has enough at the moment present within it, such that this equation will still actually hold. And indeed, if you take your Klein Gordon equation to have the form of a plane wave, and this isn't really completely just kind of extending Schrodinger's equation to relativistic quantum mechanics, because although yes, plane waves are allowed by Schrodinger's equation, we saw that plane waves, particularly plane waves associated with light, is a valid solution to the Klein Gordon equation, at least for m equals 0. So it's not outlandish to just go, well, a valid solution for the Klein Gordon equation, perhaps, that will contain all the information we need, would be a plane wave equation. And so we've got a plane wave equation for our Klein Gordon field. And if you use the Klein Gordon equation itself associated with that, you can actually prove that if we use Schrodinger's, if you like, definition of forecurrent, then indeed forecurrent will be preserved. So the four gradient or space-time version of the divergence of our 4 vector will be 0. And this therefore goes, well, if you're prepared to accept that a solution to the Klein Gordon equation would be a plane wave and prepared to treat that as a fairly general solution, then indeed Schrodinger's definition for forecurrent is directly compatible with the idea that both forecurrent is conserved and that our field obeys the Klein Gordon equation. So we haven't just taken Schrodinger's equation and extended it blindly beyond the realms where it should work. So the devil really, though, with assuming that our kind of our forecurrent is going to be of a similar form to Schrodinger's forecurrent, and that our Klein Gordon field is a plane wave, is what we get for the 0th component of our forecurrent, which, remember, Schrodinger, at least in Schrodinger's case, would correspond to the probability density associated with our particle. So let's see what we get for this if we look at kind of our trial solution to the Klein Gordon equation. Well, we firstly have to have an expression for the 0th component of our forecurrent, and just taking mu equals 0, we directly get that. And remember, the partial derivative with an index of 0 is referring to the partial derivative of our field with respect to time. And we'll take our general solution to the Klein Gordon equation. And here I'm including n. N will be important. It's a constant that we don't really need in the case of Schrodinger's equation, because Schrodinger's equation doesn't describe multiple particles, but we're interested in quantum field theory ultimately, which will have to describe interactions between multiple particles, in which case this factor of n would become important. For Schrodinger's equation, because it's just concerned with one particle at a time, n is just equal to 1, so it can kind of be ignored. Well, if you put in the solution of the Klein Gordon equation into your expression for the 0th component of forecurrent, you end up with this expression. And the problem with this expression is, well, firstly, this expression we're assuming is valid in the context of quantum mechanics, albeit relativistic quantum mechanics. So all solutions, all versions of this kind of equation in the blue box have to be true. We can't just have some of them being true and some of them not being, because that would violate one of the principles of quantum mechanics. And because we started with an equation that ultimately had e squared in, and when we derived Klein Gordon's equation, we made explicit use that we had a Hamiltonian squared. We didn't write it in terms of just a Hamiltonian. that means that E here, so our eigenvalue associated with Hamiltonian, but for a relativistic particle, would have to be allowed to be positive or negative, because we had an expression for E squared which was positive, but that means that there are two possible solutions for E, one which is negative and one which is positive, because the square root of a number will always have a positive and a negative solution. Therefore, we have to worry about the possibility that E is negative. But remember, J0 is meant to represent probability density, so now we suddenly have probability density. Now this problem doesn't arise in Schrodinger's equation, and you might wonder why, because in Schrodinger's equation a plane wave is a valid solution, and also we're using the full current as described by Schrodinger, or at least in the context of Schrodinger's quantum mechanics. But the thing with Schrodinger's quantum mechanics is he doesn't use a relativistic version of energy. He uses a classical equation for energy, which isn't written in terms of E squared, it's just written in terms of E. Particularly, the Schrodinger equation is derived assuming E equals p squared over 2m, or a quantized form of that. So in short, the only solutions for E that are possible is positive values for E. But because we began when deriving the Klein Gordon equation with a relativistic equation for energy involving E squared, our solutions for E are allowed to be positive or negative, and consequently we have to worry about negative values for E for the current density. Sorry, for the probability density. And so we have negative probability density, and that seems somewhat problematic. In fact, it is very problematic. And it's actually Feynman that came up with a possible way around this. Now, Feynman's solution is not very aesthetically appealing, which is again one of the indications that something has gone slightly wrong with Klein Gordon's equations. The Klein Gordon equation. Thankfully, there's only one of them. But, you know, it's worth saying Klein Gordon equation does well with describing pions, does pretty well with describing photons, but it does seem to struggle. When we're trying to understand the Klein Gordon field as some kind of field associated with matter particles, in the same way that, you know, the wave function is associated with matter particles and therefore has some probabilistic interpretation in Schrodinger mechanics. So Feynman's solution is a little technical. In fact, it's very technical, so I will gloss over it here and at times possibly not be too accurate. It will turn out that really won't matter, because Feynman's idea was to solve this by suggesting the negative energy states are related to antiparticles, but we'll see that a more accurate description of antiparticles is given by Dirac's equation, therefore me being a bit slapdash here isn't going to be problematic for our journey moving forwards. It's just worth me saying this because the book does go into more of the nitty-gritty. You know, and well, if you would like to research it more, it's worth saying I am going to be slightly slapdash here. But as I say, it won't be problematic for our progress, but it's worth saying that you can kind of deal with the issue of negative energy, negative probability states via Feynman's interpretation. So, when we had negative probability, it's worth saying that that was linked to there being allowed negative energy states of a particle. So we have a link between negative energy and negative probability, which might make it sound like we can't actually separate those two things. However, we can, because when we were doing things like taking the partial derivative of our field with respect to time, we assumed time was going forwards, i.e. our particle was going forwards in time. If time is going backwards, then actually negative probabilities will start to become associated with positive energy states. But if we allow negative energy states of particles which are going backwards in time, suddenly there is positive probability associated with them. And so, providing we're having, the solutions of negative energy to actually refer to particles going backwards in time, then there is no issue because we don't have any negative probabilities. And a way to actually get a particle to be in some sense time reversed is to essentially just flip its charge. And you can think of that if you think of field grinds, because field grinds are used to describe whether something is positive or negatively charged. Now, by convention, but it's only convention, if something is positively charged, field grinds go outwards from the object. If something is negatively charged, field grinds go towards that object. But if we flip time, then, let's say field lines that were going out from the object now suddenly go in, go towards the object. In other words, we've essentially flipped the charge. And that's using a very classical idea of charge and field lines, but it works even in the context of relativistic electromagnetism, as you can verify using the equation we have here, which is a legitimate equation in relativistic electromagnetism for the force on a charged particle, where if is a tensor, the electromagnetic tensor, which I talked about briefly at the end of the video on tensors. So I did a video on tensors, talking about what tensors are, different types of tensors, and as an application I talked about Maxwell's equations, and this F appeared there, this electromagnetic tensor, which I think at the time I talked about as Maxwell's tensor, because it goes by very many names. But you can make this argument rigorous if you want to, so it's worth showing the equation just in case you wanted to look at that. But now we've covered everything we need to for this video. So we've seen that the Klein Gordon equation can describe force-carrying particles. We've seen that the Klein Gordon equation struggles to describe, due to issues with probability, particles with negative energy associated with them, but we've also seen that Feynman kind of gets around this by suggesting that negative energy particles are actually just particles with opposite charge, which are going backwards in time. Or that particles, if you like, you could also think of it particles with the same charge but are going backwards in time, so it looks to us like that charge has been reversed. And this leads naturally to the idea of antiparticles, because antiparticles are like their particle counterparts but just with opposite charge. So it seems that somewhere in relativistic quantum mechanics, antiparticles are being predicted as almost a natural other half of particles, in that because particles are permitted, so we're considering Klein Gordon's equation seriously when E is positive, because of then the rules of quantum mechanics, we also have to take E being negative seriously, which leads to the idea of antiparticles in a kind of vague sense. And that wasn't a feature in non-relativistic quantum mechanics, because you don't have to worry about solutions where E is negative. So antiparticles come up as kind of like the other half of, if you like, the solutions to particles, and that is something we will see carried forward when we look at Dirac's equation. So to summarise with what we have done, the Klein Gordon equation describes force-carrying particles well, so things like the photon, and also the file. But it doesn't seem to describe matter particles very well. However, it does kind of lead to the idea of antiparticles, which is a good thing, because we'll see that when we look at more natural ways to do relativistic quantum mechanics. But we also saw that probability doesn't seem to be working very neatly in the context of relativistic quantum mechanics. So perhaps probability isn't a good conserved quantity. Perhaps this field, this Klein Gordon field, can't be interpreted with the same probabilistic ideas we use to talk about Schrodinger's wave function. And indeed, we saw that actually our field seemed to be describing force-carrying particles. And when we kind of quantized force-carrying particles, when we quantized the potential referring to forces before, we saw the emergence of force-carrying particles, which related to the idea of creating or destroying particles. So we might start to think that actually the number of particles is a better conserved quantity in relativistic quantum mechanics than probability. And maybe probability starts to have difficulty because in quantum field theory we are creating and destroying particles. And maybe in some way keeping the total number of particles fixed. But particularly if we're considering forces, we want the total number of particles over a sufficient amount of time to be fixed, because we don't want to permanently create particles. We can have force-carrying particles, but if they appear, they need to vanish fairly quickly, because otherwise objects that kind of had forces associated with them would generate a large number of particles that wouldn't vanish, and that would be very clearly observed, and we don't see that. But because we're having particles appearing and disappearing, probability starts to become a harder thing to define, because it's like, well, the probability of what? Because the probability of finding a particle in a particular state, for example, can now be stop being conserved, because the particle can just stop being present. So the probability can go from 1 that we'll find the particle in some kind of state to 0, because there is no particle there to speak of anymore. So that's a hint about where we're going. It's a bit abstract for now, because we're kind of looking at Schrodinger's equations, Klein Gordon equation, trying to stretch to see where might this quantum field theory be going, or where might relativistic quantum mechanics be going. But it's worth keeping these insights in mind as we move on to next. I think we'll look at writing down Lagrangians, where we'll see the Klein Gordon equation is a possible solution to a particular Lagrangian. And then later we'll look at Dirac's equation, where we'll explore matter particles more properly.